Okay, so today we have our own Kris Brown. He's our resident expert on graph rewriting and rewriting of other categorical structures, and so he's been working to improve the performance of his system, a key component of which is finding homomorphisms between Copry sheaves. So he's going to tell us about his efforts around incremental hom search to make this much faster. Thanks, Kris.
Thanks.
Yeah.
So, so to provide some context for the problem I'm trying to solve, often, we care about, we have some state of the world and we have a query for it. So here we're going to represent our query as some pattern called X and our state of the world, which might be G. And what we care about is what are all the homomorphisms from X to G? And of course, this is very broad because a category is very amorphous. There's lots of things which are categories. An important kind of problem is that G is changing. And we want to say, well, I want to know how my hom set changes. So we might have some update from G1 to G2. And I want to know, well, I had hom G1, hom X to G1, but I want hom X to G2. And if all we have is that sort of extensional difference, like these are all the facts in G1 and these are all the facts in G2, that's a sort of well-studied problem of how do we do this incremental update to our query, where I just have a raw extensional difference. But what I've observed in a lot of my work is that often we have more information. Not only do we know what changed, but we know why it changed or how it changed. We have some abstract thing, which we might call a rewrite rule, which sort of sets the pattern of what was the kind of change that happened. And so not only do we have an extensional difference, but we have sort of an intentional difference. And so in category theory lingo, we have a rewrite rule, let's say, which is a morphism. And we applied that rule to some state of the world, call it G1. And we got an update by applying that rule. So not only do we have the update, but we know, well, it came from this rule. And that application happened via pushout. So given that we have this extra data, can we do something that is even smarter than what we could possibly do with just the extensional difference? So again, I have all of my morphisms into G1. I want all the morphisms into G2. Now, every single morphism into G1, if I just compose it with this update, delta, I get one. So I don't care about those. Those are the old ones. Those are the boring ones. I want to find all of the X to G2 morphisms that are not in this hom set post-composed with delta. So that's just the overall setting of what I'm going to talk about. I also maybe should mention some motivational context for this. So a lot of this came about from working in agent-based models, where we model a state of the world as a C-set and possible actions agents can take or events as these rewrite rules. So, but we're also noticing that potentially in E-graph equality saturation that we have a fixed set of rewrite rules, and we can use those. We also want to be monitoring these hom sets, which are telling us which rules can we possibly apply. There might be an application in data log that's analysis, and also in Cat Colab, which we're developing. There's lots of affordances that will come about from having knowing what certain hom sets are. And these models are being changed real time by users very frequently. So if you had to relaunch an entire hom set calculation every single time a user edited one little part of the graph or the model, that would be unfortunate. So I'm hoping that by working at a quite general level, that we'll be able to apply these results in lots of different contexts. So, yeah, questions are fine.
How do you know the difference between an old map and a new map?
How do we know the difference? You can just check, is it equal to, because we already know the set, and I know this update. So I can just check, is it equal to something that I already had composed with this? Our goal is to have an algorithm which finds all these and only these, so that we don't have to do this check, oh, did I find duplicates with my old things? So yeah, by construction, we're going to avoid those maps. And in this document, I sort of go through in a sort of linear order, which I, upon reflection, decided was not a good idea. I want to take some very parallel structure to this talk, where I talk about some concept informally. I want to give a sort of general description of it for an arbitrary category, perhaps with some extra structure. And then also, at the same time, for every single little piece of the story I tell, I want to say, what does it look like if we just consider the category of sets and functions? what does it look like for a C-set category in particular graph. So I'm going to try to fill this out. Occasionally there will be something that's too big, and then I'll have to defer to my existing table, which I'm going to try to reproduce. But we'll go to that if we have to. So the start is, and I had a marker, but OK, well, I was looking for a black marker. Ah, great. So to do this parallel thing as an experiment, we have a problem domain, which is a category in general, but in the set example, it's just set. And in our C-set example, it's just graph. So we need a pattern to work with. So a pattern is just an object in your category, which in the case of set is just a set, or is just a C-set. So our set example is going to be this 2-element set AB. And our graph example is going to be this pair of composable edges, so a path of length 2. Now, oh, I realize I should have done screen, not screen mirroring, but screen sharing. Sorry, I should not have done screen mirroring so that you don't have to see. Let's see if I turn this off. Yeah, this is supposed to be just the context for people who want to look at that. And I'm supposed to see this other thing here. OK, cool. So we have our pattern. Now we have the idea of a rewrite rule, which I'll say I'm just going to consider additive rewrite rules. Additive rewrite rule. This is just going to be a morphism in our category. And we'll say it goes from something L to something R on the left and the right. And so this will just be f a function. And our example function will take a singleton set with an element called 2 in it. And it will send it to a set 1 and 2. And this will be a C-set morphism. C-set morphism, which is just a collection of functions for every object in our schema. And here we're going to send an edge to a little triangle. So we're looking for an edge. And when we see an edge, our rule is, well, what if that edge were actually a triangle? And so we add an extra vertex, and we add 2 more edges to it to make the triangle.
Question?
Sure.
When you say C-set, you mean just co-precisions on any category C?
Yep, some finitely presented category C. So yeah, this is,
Finitely presented?
yeah. So this is just our stand-in for like a database where the schema is C, for people who haven't seen that story before. I am presupposing some Topos common lore.
And the map from the arrow there is the one that doesn't rotate it?
Yes, I'm going to actually take these as like embedded graphs. The data of the morphisms will sometimes be implicit in their orientation. Great. So now I want to say, what is an incremental update? An incremental update, and now I'm going to see if I can draw straight lines under pressure. OK. No. OK. Incremental. An incremental update, in general, is just a push-out, as I showed earlier in the sort of preview. So I have some state of the world, G1. I get some state of the world, G2, out of this. And I'll just name things like this, where M stands for match. We apply the rule by matching our pattern somewhere in our current state of the world. We do the push-out, and we get this extensional update, delta. And we also get a map that tells us where did our replacement of our rule land inside of the new state of the world. So this is just a push-out in set, and this is just a push-out in C-set. So what's our example? We have 2 goes to 1, 2, goes to 2, 3, 4, goes to 1, 2, 3, 4. And here we have our rule. And we're going to apply it to this graph. And we're going to get this graph. So we've added the triangle to these two vertices right here. So this is like, we'll call this new, and we'll call these edges, or these vertices 1, 2, 3.
Can I just double check my understanding of the set example?
Yeah.
So I think about like, usually write your rule on the left-hand side. So this is like, I have a system that's like 1, 2, and the rule is like add 3, 4 after 2.
No, the rule is if I see this thing, which I'm going to label as 2, and I'm going to add 1 to it.
Okay.
And I'm just using the names to also help us give you the data of the morphism. So I'm going to match 2 to actually this element also called 2. And that's going to produce a set called 1, 2, 3, 4, which 2, 3, 4 are in the old database, and 1 is in the new database. Great. So now the incremental search problem is informally incremental search problem. Informally, I'll say what the formal thing means, is that I have hom x g1 want hom x g2 minus hom x g1 post-composed with delta. So the hom g1 post-composed with delta gives us all the old matches that we already knew existed. That's not interesting. We want the new ones. And so this means I have 2, 2, 3. Sorry, I have 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4, 4, 2, 4, 3, 4, 4. And I want 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 3, 1, 4, 1. And over here, I have 1, 2, 1. So I'm going to just give these maps from my path graph just by saying what the vertices go to, 1, 2, 3. So I have 1, 2, 1, which goes from here to here, back to there, here and back. I have 2, 1, 2, and I have 1, 2, 3. But what I want is now what are all the new paths of length 2 given this updated state of the world? I want 1, n, 2, 2, 1, n, n, 2, 3, n, 2, 1. Yes?
Are you only considering pushouts where the left side is mono?
Yes. So also, yeah, at the end, sorry, now I actually have to switch if I want to show this. Oh, how can this be so hard to
It might not know where the edge is.
oh, maybe it's because it's full screen.
I'll do a video as far.
Yeah. And now, yeah. So at the bottom, sorry. At the bottom, I'll say directions to go from here. Why would this produce a fast algorithm? Actually, this is nice to know the sort of like follow-up questions once I tell the basic story that these are the 4 sort of directions we could go based on people's curiosity. You know, why is the story I'm going to tell produce a fast algorithm? What about applying rules where this match morphism isn't monic? That's exactly your question. What about deletion and merging? People think rewrite rules can do those. Why is the thing I'm going to show you correct? I have a proof sketch that we can go over. And if you've seen my previous work on this, the algorithm I'm going to show today is a little new, and why is that? So that's something that we'll be working towards once we just finish what is the basic story. So yeah, that's all to say, great question. I will talk about that later. So yeah, I'm assuming that M is monic. I'm assuming F is monic. And that is going to make things easier for us. Great. So I've said informally what the problem, but you know, there's something very interesting here, which is what does it mean to like I want these homs? Like how do I find these homs? What does that even mean? So for that, I need to tell you what a specification is. Sorry, I've not been drawing my horizontal lines. So a specification of a Hom set. Specification of some sub-Hom AB. In general, I'm going to say this is an internal relation. So that's a monic map into A times B. And this can be evaluated where F is in R, let's just say EVR. So we can evaluate this morphism to get a subset of this Hom set, and that's if F is less than R. So if we interpret F, every morphism can be interpreted as an internal relation by taking the graph of the relation. And so we can say, well, if I have an internal relation, I'm implicitly talking about all of the functions which are less than the sort of lower set in this lattice of this relation. So I'll try to show, sorry for the hard to see with things in the way. I'll try to show this by example, and then this is an important point, so I do want to get questions. So in
Can you, the notation V sort of appeared out of thin air.
EV, sorry, EV, like evaluate, like there's actually a right adjoint from internal relations to the power set of this Hom set, and I'm going to just call that EV. It's going to send an internal relation to all of the Homs that it is specifying. Right. And so yeah, maybe an example. So a specification of some subset of some functions is a relation in set. So if I have A, B, and 2, 3, 4, and I just have these elements in my relation, this is a specification of 2, 2 and 2, 3. So for this Hom set from, this is from X to G1. So we're looking at all the functions from A, B into 2, 3, 4. I can say this relation picks out just these two out of all 9 of them that exists, because I'm saying the function 2, 2 looks like this, the graph of that function, and the function 3, 2 looks like this. So this relation says I want those two functions and none of the others. The story goes the same in podium. Sorry, yeah, I didn't realize I was going to go that low. Okay, so is that better? Great. So this relation here is picking out these 2 elements out of the 9. In C set, we have a pointwise relation. And perhaps we could say, if I have some R sub V, let's look at maps from this walking edge into our state, our G1 again. We'll say the walking edge has vertices 1, 2, and this graph has 1, 2, 3. And what if I say that 1 has to go to 1, but 2 could go anywhere? And maybe R sub E is just the top relation, so everything is allowed. This specification would pick out all of the morphisms that send this vertex to that vertex, of which there are 2. There's 1, 2, 3, and 1, 2, 1. So this is a pointwise relation, of a relation for every single object in the schema. Hi.
Sorry, can you, like, I've sort of lost, can we go back to the set example?
Yeah.
Sorry. What are A and B, what should I think of when capital A and capital B?
Oh, yeah. This is the domain and codomain of the function. So I'm looking for, there's a Hom set, Hom AB, capital A, capital B. I'm talking about how do I pick out subsets of that Hom set.
I think I get that, but I'm like, should I think of A as your pattern and B as
Well, there's going to be multiple different relations in play, actually. But yeah, certainly the relevant one is I want to ultimately end up with a relation on x times g2, because that's going to say I want some relations. I mean, I'm going to need multiple of them, but I want some relations which, if I evaluate them, I get exactly this thing that I want. That's how I find those homomorphisms. Yeah.
Why does the category have products? Is that just an assumption that was?
Yeah, sorry, great. This is an important thing. So we're going to say, I'm even going to say it's like by complete and adhesive. So we're going to be adding conditions as I need them.
Yeah, he was also assuming, I think, that push-outs of
Yeah,
models were.
exactly. Right.
Yeah.
I mean, do we need to even muddy our heads? Can't we just be in CSET?
Yeah, in my motivation, I was like, there's other categories that are important too that are very CSET-like, such as, e-graphs, but I do want to consider how general can I go, and that's one of the open questions at the end. What did I really assume in this process?
Can I paraphrase the answer I got from what you just said?
Sure.
I'm like, okay, the result of an incremental search problem is like a subset of these HOMs. And you're like, how might you specify those? You might specify those as a relation.
Yes. And it turns out there's not going to be just exactly one relation that carves out exactly hom xg2 minus this hom xg1. So I'm going to need probably multiple relations that if I just that will partition that space. I want to get everything in the set, and I don't want duplicates, but I'm not going to be able to do it with just one relation. So the next row will say incremental search problem formally, and it will just say exactly that. It will just be give me a set of internal relations such that if I evaluate them, I partition this thing that we want.
Cool.
Great. Maybe I don't even have to write it. I don't know. Let me see if there's anything beyond that.
Sorry, I think I also interrupted you in the middle of your example.
No, oh, yeah. So this was just to say, here's a pointwise relation. It's a relation on V and a relation on E. Note that if I just give the top element of this lattice, I'm basically saying give me the whole HOM set. So I'm saying there's no constraints on E. There's a constraint on V that our first vertex in our walking edge has to go to vertex 1 in this thing we're looking for HOMs into, and I'm putting no constraint on 2. This is how we sort of interpret this language of specifying sub-HOM sets.
I don't understand how this is.
Yeah, you?
I don't understand how this is a relation in graph. Shouldn't it also say which edges you have?
Sorry, this is, I'm saying this, my relation on edges is the top
okay.
element,
I
yeah.
didn't understand the notation, sorry.
Yeah.
That makes sense.
Any?
So what are you going to do with that lattice?
What am I going to do what?
With that lattice? Like you have specificity on like which elements you pick
Yeah.
out. What are you
So
going to do with that lattice?
it turns out, this is nice to think in the CSET example, that this internal relation you could think of as initializing a backtracking search. So I'm going to do backtracking search for my pattern, but I can
check off which ones you have.
Yeah, so the interface of backtracking search says you're allowed to initialize things, you're allowed to sort of like carve out acceptable regions to make assignments, and to sort of spoil why is this fast. The general HOM search problem is NP complete, it's really slow, but as long as you can actually initialize even one value, you get something that's called a rooted subgraph isomorphism problem, which is suddenly scales in just the size of your pattern and maybe like the branching factor. So in general, we want to have our search, we want to convert something that scales with the size of the G2 to just multiple searches, but ones that only scale with the size of our pattern X.
Yeah, there is actually like what I just shown you.
Yeah.
There is a very neat analogy between
Cool.
this.
All right. We will say we can talk about that after then. Cool. So yeah, so it's fast because I can actually practically interpret one of these things as I can actually. This evaluation is not just abstract. At least in the case of C-sets, you can actually find those HOMs and very fast because we can initialize some values. Great. So inc HOM problem formally. I want a set Ri of internal relations on X times G2 such that EV of Ri partitions you know, hom set we want. And there's actually one other condition, because there's a very trivial way to get a solution to this, which is that I just picked Ri as the set of graphs of the functions I actually want, right? I could just bake in the solution already by just saying, oh, well, there's a very trivial solution where I just have, you know, one of the R, these are each the relations that I want if I just interpret these things. So what's really important is that we don't know ahead of time what G1 is and what G2 is. And they're also really big. So what we want to do is sort of indirectly specify this relation, because G2 is really big. So the way that I've sort of made this formal is that our relation should not distinguish between elements of G2 that are not in the image of R. So basically,
Wait, can I pause you before? You're refining something before.
yeah.
So you're trying to find a set of relations
Yeah.
such that each of the desired functions is contained in exactly one of the relations.
Yes.
And nothing undesired is contained in it.
Correct.
That sounds hard.
Well, it's easy. And I also want to say such that for all sigma, which are iso G2, G2, that, let's say, R sigma equals R implies Ri sigma equals Ri. This is saying, look at this rewrite rule application. So I'm picking out some subobject of G2 with my morphism R. I want to say I could mix up all the elements in G2 in any way I want, except the ones that are in this image of R. And my relation should not change at all. I shouldn't be able to distinguish between, you know, if there's a million elements in this set, you know, my solution to this problem shouldn't be able to make any distinction between elements 73 and 423. I should really only be able to distinguish things at the scale of my pattern. So let me show some examples. I'm going to write the solutions to the problem in this row, actually. Now I have to do a lot of walking back and forth.
You don't need any condition on the join of all these RIs together cover this?
I'm saying, I say it partitions. Yeah.
Sorry,
So 1 and 2, 3, 4.
Kris, do you mind writing a little bigger?
Yeah, sorry. So R 21, 31, 41 is a relation, internal relation on xg2. So that means I have AB here, and I have G2, which is 1, 2, 3, 4. But I'm going to put 2, 3, 4 in a box together because I really can't distinguish. At the very least, this says I can't distinguish 3 and 4 because they're not in the image of lowercase r over there. So I'm going to say I'm going to send B to 1, and I'm going to send A to something here. And here's another one.
What is lowercase r here?
Lowercase r is right here. This is saying when we apply the rule, we get some subobject of our rewritten. A concrete example here. So this is the image of R, and
No, just one at a time. I think, probably. Because you're in the middle of talking about
I'm talking about set, yeah. So I'm saying this condition here is saying I can't assign a different element to 3. Like if something's in 3, it's in 4 too, and if something's not in 3, it's also not in 4. I'm saying I'm tying a hand behind my back. I'm saying I need to give relations which don't distinguish in the the part of the graph that's completely unrelated to the rewrite that I'm applying.
And
Because if I could do that,
the notation there is you're saying I'm relating A to 2, A to 3, and A to 4.
yes. So you could imagine this as this, but I'm
Wait, but I thought 2 was also part of. I thought 2 was also part of the image of R.
2 is in the image of R. I'm just saying I can't distinguish 3 and 4, but I'm saying I'm going to give a solution that has
Oh,
3 parts.
It's just that I thought you were grouping 2, 3, and 4 together.
Yeah, it looked
Oh,
like
yeah.
you didn't have those.
Yeah, sure. I should probably do this.
Okay, that makes more sense to me.
So our 1, 3, 1, 1, 2, 1, 3, 1, 4 has 1, 2, 3, 4, and A, B, and that just has a 1 here, and B goes to 2, 3, and 4, and then R1, 1, this one only picks out one element of the Hom set that we actually care about, and that just sends both A and B to 1. So I'm going to say this is a solution to our incremental Hom problem. And I've stopped.
Because these partition the space of the new morphism?
Yes, these give us all and only the new morphisms, and there's no overlap between them.
And we know the things we wanted. That's right there in that.
Yeah. So we wanted these seven morphisms, and one of the three relations got these three, one of them got these three, and then another got that one.
Sorry, I think I got a little owned by the fact that the pattern and the sort of domain of your functions look identical here.
The pattern and the domain.
Like they're both two-element sets, and
Yeah. I agree. You could. Cool. Let me see if I can show at least one of the solutions for.
Sorry, you know,
RV, let's just say the first one is we're looking for a relation from X, which has 3 vertices, 1, 2, 3, into G2, which has 1, 2, 3, 4. It has N, it has 1, it has 2, and it has 3. Note that our condition here, 3 is the only vertex that's not in the image of R. But there's only one element here, so this sort of like permutation thing actually doesn't apply. But if there was 20 other vertices in this graph just randomly elsewhere, then we wouldn't be able to distinguish them with our relations. And so one of them says our second vertex is going to be the new vertex, and the other ones can go anywhere that isn't a new vertex. Another one, and this one we'll have as our E sub 1, we have actually two new edges, which I'll just call N1, N2, and there's 3 old edges. And we're saying, actually, the first edge of our path graph is going to go to our first new edge, and the second edge of our path graph is going to go to our second new edge, this one and this one. So this particular relation actually just carves out, it's sort of like if I was initializing a Hom search, but I got the whole morphism for free. When you apply this rule, you basically don't even have to look at the rest of the graph. You just get one path of length 2 for free. But the other ones might be more interesting. If I have, let's say, our second relation, N1, 2, 3, 1, 2, 3 for our path graph, we'll say, oh, well, maybe our new vertex is the first one. And the other ones could go to any vertex. And our E2, N1, N2, 1, 2, 3, 1, 2. Sorry, I'm not writing big again. And we're going to say the first vertex goes to the second new edge created, and the second edge could go anywhere. So what does this look like? This says we're going to say, well, there's another whole class of new Homs that start at N. They have their first edge being the second edge we generated, and then it can go anywhere from there. So, and then there's a third one that says, our new vertex is our third, the third of the end of our path graph. So the algorithm that I want to show, if I have time, I'm not running out of time, is how do I mechanically generate this, and even in an arbitrary category?
I know you're already running out of time, but I invite us to all think about this for 30 seconds, because I feel like you just presented a lot very quickly.
Great. So yeah, so these were,
It's on my clock.
and I'll say and example solutions. So what I did in this row was say, formally, what does it mean to, what is the formal problem I'm trying to solve? And then I give solutions. There's a third one here, which I'm not doing.
Maybe we can try to figure it out.
Yeah, we could try to figure it out. Okay.
No, not you.
Yeah, no, I'm saying, yeah. I was just going to draw the scaffolding. 1, 2.
30 seconds of silence.
So,
isn't there a problem here?
Okay. If you guessed this, you were right. We're saying that the third, the sort of, we have a path of length 2. Our third vertex is the new vertex, which means our second edge has to be this vertex, this edge we just created, and then we can draw from anywhere else. Everything else is unconstrained. So, I mean, this was kind of cruel to make you try to do this in your head before I show you how to do it. But, I mean, yeah, there's intuition. Like, the algorithm was motivated by intuition of just like, oh, this seems obvious. Like, how do you formalize it, though? So let me, it seems like all my extra questions we won't get to, but hopefully I'll be able to just show you the solution. So solution step 1, and this is done at compile time. So solution 1, part 1, compile time.
When you say solution, you're like, how do I come up with these incremental?
Yes.
Search space
Is it
generation.
Is it fair to think of these as disjunctions of conjunctive queries?
Yeah, probably. Yeah, that looks right. At least in the C-set case. So it's up for grabs what's going on in the general category theory part. So I'm going to compute hom x co-kernel of f. So what is a co-kernel? I just looked at it. I mean, I figured out what this is first, and then I Googled, and I was like, oh, wait, there's a name for that. So if I have L goes to R is my rule f, and I send L to the terminal object, and then if I take that push out, I get something called co-cur of f. And I'm going to call this I1 and IR. So now I'm saying the solution to our problem is actually all wrapped up in all the maps from X into this co-kernel thing. And actually, these are going to correspond to our relations that we care about.
Here's our rewrite rule.
F is our rewrite rule, yes. Actually, one of these morphisms actually correspond. We actually partition the entire hom set, not just the part we want. And exactly one of these morphisms corresponds to all the morphisms that we didn't want. That morphism is sending X to the terminal object and then taking this inclusion. So to get some intuition for this co-kernel, I guess I could show you the examples in set and graph. But this terminal object, is basically representing all of the not new stuff in the graph.
That's what you subtract out there?
Yeah, so I'm going to say, I'm going to get a relation for every single hom in this hom set from X to co-cur. And one element of that hom set is going to be a relation which actually, if I evaluate it, if I evaluate that relation, I'm going to actually get hom x g1 composed with delta. So I just ignore that one, and I do what I'm going to do. I do this evaluation thing for all the other ones. Incidentally, that is the only relation which will not correspond to something where you initialize any of the values.
And this sounds, in some sense, circular, but the point is that like f is tiny and g1 to g2 is big, and so this is free.
Exactly. So this is usually even smaller than R. So I can solve this problem. Not only is this a small problem, but I'm doing it at compile time. I don't even need. I can pre-do all this work before it's even show time.
What does co-cur of f look like?
That's a great question. So in the case of sets, this is I take some bottom element and I union it with R minus L. So this is the new stuff. In the case of our rewrite rule, this is just 2. And then I say, and there's some element bottom which is bad. This is old stuff.
Partial maps in your old approach came from.
Yes, I think so, yeah. There's a very close relation. My old approach involved finding all the partial maps from X to R, and there's obviously some vibes between partial maps from X to R and X to R plus 1, where the co-kernel is kind of like R plus 1. Yeah. If there's a formal equivalency, then that would be interesting. Anyway, so in the case of our example, this is going to be the set. We have an element 1 and an element bottom. I called it bottom because I didn't want 1 and 1. So this is our co-ker equals co-ker F. And over here, co-ker looks like this. And I'm going to call this one new, and this one bottom vertex. And so what are all the homomorphisms? Well, what are all the homomorphisms into this from our pattern X? We have bottom bottom, we have bottom 1, we have 1 bottom, and 1 1. And I said, this is the bad one. This is the one we don't like. It sends everything to...
Do you not collapse that self loop?
No. OK.
There's no such thing as collapsing a loop in a directed graph. There aren't identity. That's as collapsed as it can get.
OK. And over here, what are all the maps we have from X into this? Well, again, I'm going to identify these by just the vertices. We have n bottom n going this way. We have bottom n bottom. We have bottom bottom n and n bottom bottom. And then there's also bottom bottom bottom, which is just bad. We don't like that one. This one will recover all of the old homomorphisms. Once we convert these morphisms into a relation this. So we have to do some processing to do that. Yeah?
Sorry, can you show me why, in that case, why bottom bottom is bad, but bottom 1 is not bad?
Yeah, well, I guess I haven't shown you how do I interpret one of these morphisms from X to co-ker X as a internal relation on X G2. So it's not yet clear what the meaning of this is. But there is... yeah, I mean, there is a way of seeing that when I apply my rewrite rule, I also have a map G into R, right? Sorry, no, I don't. I have a map G1 into G2. And so what I care about is maps X into G2. And there's a construction that basically tells you, there's a general, sorry, there is a general function, a morphism, universal map from G2 to co-ker, such that if I compose, this is the morphism I really cared about, right? I'm looking for Homs X into G2. And there's a universal map from G2 into co-ker. And it turns out, yeah, I guess this isn't really answering your question. If you do compose these two maps, you basically get this morphism that, the morphism which would have found this morphism. This is, maybe I'm jumping the cart too early because I haven't told you how do you actually get one of these relations we care about. OK, there's only 3 parts, and the third part is just one word. So let me see if I can do solution part 2. This is construct internal relation on co-ker F times G2 given our incremental update. So this is a match, a rule, an update, an R. So given the data at runtime of our rule that we just applied, I'm going to tell you there is an internal relation that we can universally construct on this. And what does that look like? Well, there's a formula, and it will be scary, and it's into, actually, maybe at this point I'm running out of time, so I'll just start going to this. The one difference between my chart up here is that this first column is at the end. It says informal set example, C set example, then general. So just reorient your mind that this second column is now at the end. So, and maybe I'll go bigger. Sorry, where is my? OK. Oop. So solution 2. This is what this relation on co-ker times G2 looks like for our set example. So co-ker has a new element, and it has all the old stuff. And so we're going to say, well, the new element should go to the new element in G2. and the old stuff should go to all the old stuff. Likewise, in C-set, we have now a pointwise relation where I have, again, I have a new vertex and an old vertex in my co-kernel. New vertex, old vertex. And we're saying this relation is going to say, well, the new vertex is related to the new vertex in G2. That's what that check mark is. And then the old vertex, basically the vertex in the image of 1, the terminal object, can go to anything else. And likewise for edges, I have the new edge 1, the new edge 2. Those go to the new edge 1 and the new edge 2 in G2. And then the loop, which came from the terminal object, goes to everything else. So this is and if you wanted a formula for this, it would be this. And then I can take a question. So the general formula is this co-pairing of this pairing of morphisms and this Cartesian product of morphisms. And if you were to sort of like generally look at what this relation looks like, we're saying, you know, the co-kernel has some stuff in R. It has some stuff in both R and I1, which is the terminal object, and it has some stuff that's purely in the terminal object. And G2 has some stuff that's in R. It has some stuff that's in delta and some stuff that's in both. And what we're doing is we're basically unioning together two relations if we are thinking set in a set-like category. And so you basically have this diagonal relation and this complete relation. This is what this formula is telling us. This is kind of like, this is the abstract picture of what is this relation that we can universally construct. Sophie, do you have a question?
I more like wanted to tell you that I'm quite lost.
Okay.
And one idea that I have, it's fine if I'm lost and other people follow.
No worries.
Do a quick poll.
Yeah.
Do you want to close your eyes?
No, it's fine. I'm going to presume everyone's lost. Okay, so the idea is that I wanted to solve this problem by getting a bunch of relations that have this nice property. Those relations corresponded to maps from X into the co-kernel. And I'm trying to describe how do I take a map from X into the co-kernel and get a relation like this. It's two steps. One is I interpret this relation as a graph. So this is an internal relation on X co-cur F. The next step is
You mean each HOM is?
each HOM is a relation, internal relation on X co-cur F. Then I say, given the incremental update, there's a universal relation on co-cur F times G2. And if I just compose those two relations, part 3 is compose, one word. If I compose those two relations, I get my solution to the HOM search problem.
You compose that relation with each of those.
Yeah, so I've got all these different relations X to co-cur. In each of those, if I just post-compose it with this one universal relation, which has this ugly formula of IR paired with R, and then I1 times delta. It's not that ugly, but if I post-compose this relation with all of these, then I actually get the relation that has this property. And yeah, you also don't have to do this explicitly, because I mean, the whole point was we wanted to avoid doing anything at the scale of G2. We wanted to be working at the scale of L and R and X. So this is just describing formally what's happening. Yeah. Michael?
Can I do a quick check of my understanding?
Yeah,
of
yeah.
This? The co-cur thing is sort of a schematic condensation of there's one object representing all the old stuff, and then there's objects for all the stuff that was involved in the rewrite rule.
Yeah, one sub-object. Yeah, it's a push-out mnemonic, so it's jointly two sub-objects which have some intersection, but one of those sub-objects represents all the old stuff. Yeah, because I got...
Bottom in your first example represents all the old stuff.
Yeah, so it's anything in the image of this inclusion from the push-out, yeah.
And then if I look at maps from my query into this schematic, those will nicely partition all the ways that I could get an actual match in the full G2.
Yes.
Right, where I think of bottom or the stuff representing the old stuff as being a variable standing for any old stuff.
Exactly.
Right?
And yeah.
And so this partitioning is what's giving me the partitioning of relations.
Yes.
That I'm gonna, okay.
Exactly. Yeah.
So if I see how you get these asymptotics if you with the assumptions you laid out. What I'm interested in, does this coincides with the naive way of doing it if delta is like on the order of size of G2?
Yeah, so so I assume delta and G1 and G2 are all, millions, they could be, bazillions big. And really, you should be able to just take this map, this map from X into co-cur F, which is everything is small, and automatically generate your sort of constraints on your incremental on your backtracking search, for example. So you don't actually have to construct this thing, which would defeat the purpose, because this is huge, yeah. But you can view this morphism as a presentation of this internal relation in this way.
Like a sort of encoding that you can use in your search algorithm.
Yeah.
Without
Because I know what things to be free variables because they go into this image, and I know what things that get pre-assigned wherever R tells me to assign them. Yeah. Good, Evan?
So this universal internal relation that you construct on co-cur F times G2 comes from the co-pairing of two things.
Yeah.
Is it possible to give an intuition of what each of those things is doing?
Yeah, one of them is this diagonal, and the other is this sort of block.
Right, but like
Oh.
why?
Why? Okay, so the diagonal is saying R, lowercase r, is basically saying how does R, the right-hand side of our rule, embed into the actual graph? And we're saying pair that with this map IR, which is saying we're pre-assigning, we're basically initializing these values based on what got sent to actually new material. And this full Cartesian product of two morphisms is saying, delta is saying all the old material, right? That's the map from G1 into G2. And I1 is basically saying this symbolic representation of the old material. Everything in that also gets pairwise.
So the first part is what you're committing to based on the map into co-cur from X. And the second part is what you're allowed to assign freely after that or something?
Yeah, I mean, the first part is kind of like, what's the intersection of my image of X and IR? And the second part is like, what do I do with the intersection of my image of my map from X into co-cur with the intersection of the map from I1? So yeah, because co-cur X has two subobjects that constitute it, and any map into that is going to intersect with one of those two images. And these two rules are saying, what do I do with those two images? And one is, you can do anything as long as you send it to the old material. And this one is saying, nope, I have a particular value I know I can assign to that because I have a map from R into G2. Yeah.
Simple sentence.
Of course.
So, okay, it's not a simple sentence. The question is, like, if our world is growing in some structured way, how do we find the new patterns that are made available in this extended world? And so what you're doing is saying, well, the pattern, if it's a new pattern, then something in that pattern must be in the new part. So we're just going to pick all the different ways some part of the pattern could be in the new part, and then we just, the rest is the rest.
Yeah. Yeah, I think that's a good way of saying it. And yeah.
That's why it's always the bot ones that are the bad ones.
Yeah.
Old.
Exactly.
But those are the only bad ones. All the rest are good.
Yeah, because all the other ones have some non-zero intersection with this image of the new stuff, which is the stuff that's in IR, in the image of IR that's not in I1. And saying words like image is sort of committing myself to like maybe there's more structure than just this. So far, I haven't really used any structure. In the course of like proving that this is correct, which will definitely not have time to do, I do have to invoke some more structure to this category, which I don't know if I actually have to, and that's a future discussion.
Like it seems like you sort of assumed it's regular.
Oh yeah, it's definitely regular. Yeah, it's definitely regular for sure. But I don't want to have to assume like it has like the bi-hating topo structure, like the internal logic of C-set type stuff. Okay, well with our what? Okay, so I guess we only have 1 minute left. So what of these questions most excites people to hear about for 1 minute? It's why should this produce a fast? I already said this. This was because we've transformed subgraph isomorphism problem into many rooted subgraph isomorphism problems. What about applying rules with a match morphism that isn't monic? That's a little niche. What about deletion and merging? Why is this correct? Okay, I guess none of these are that interesting. Anyway, what do you guys want?
finding what the algorithm that you have specified is still where I'm at.
Okay, yeah, then we're a bit.
But I don't know if 1 minute helps much with that.
Okay.
Write out some of your symbols.
Yeah. So there's like, this is like how you compose internal relations. That's not interesting to you,
Actually, you should respond to Michael. Ignore me.
Michael.
Monic. So is this about like, if I have a pattern, can I match it in a way that identifies two things?
Yeah. So this will find even non-monic matches from X. The constraint that seems a little artificial, but it's very easy to like work around. There's a very simple workaround that uses this algorithm as a subroutine, where this match right here could be not monic. The algorithm is.
What does it mean for that to be monic?
So this is saying, yeah, I'm looking like I can't apply this rule to a loop. I can't apply this rule to a loop.
Okay,
Yeah.
right. So that was
Currently.
no unexpected equality.
Yeah.
Okay.
But there is a trivial way to make this algorithm work for that case too. But
Where you do allow unexpected
Yes.
equalities?
Yeah.
And is it you split on whether things are equal or not?
yeah, so you basically you take your pattern and you look at all possible quotients of it and you do this for every single one of them. Yeah. Okay. I feel like
What we should do is
yeah, we can.
For an excellent adventure, we've gone many places.